Well, now, good afternoon. Thank you for so many of you for joining me for the next hour. I appreciate that you're taking the time to eat into your lunch hour, as it were. There's still people joining, so I'm going to do a personal introduction and then move into the material for the seminar. My name is Brad Brown, and I'm a web age instructor. I deal with a number of courses around solution architecture, enterprise architecture, data warehousing, big data and analytics, among a number of other topics. And I'm also an independent practitioner. Many of the web age instructors are independents who are practitioners in the field. So it's rather than being just course delivery, many of us are also actually working in the field and bring real-world experience to the material that we're presenting. My background, just as a way of introduction, is I've spent a very long time in Loblaws. Most of my career was spent in Loblaws, doing pretty much everything there is to do in IT. And since leaving Loblaws, I've had a couple of the C-level positions in technology companies, post-startup, a pre-public, and I've been independent for about 6 years. My practice focuses primarily on solution architecture, data warehousing, analytics. And I'm also teaching a course at the University of Toronto School of Continuing Studies on management analytics and big data. So hopefully bring a fair bit of depth to this particular topic. So I'd like to welcome you all to our seminar this afternoon, Big Data Business Intelligence and Analytics for Business Analysts. This is a 1 hour seminar which is drawing material from a 3-day course. And this course is intended to give people in a data analyst or a business analyst role a broad sense of the kind of technologies and capabilities and things that you need to consider when embarking on big data analytics inside an organization. And of course, in 1 hour, we're selecting a fairly small set of topics out of this. And what we're going to do today is we're going to walk through one of the chapters, which is an introduction to some of the underlying technologies that are frequently used in big data. So I'm going to give you an introduction to the concept of business intelligence and analytics and how it relates to what we colloquially call big data. And then some of the underlying programming techniques that have underpinned this space in the last few years, as well as a brief introduction to some of the actual technologies that people in this field are using every day. I'd like to invite all of you to use the questions. Sorry, I just saw a chat message come up. Use the chat capability for to raise questions. Normally in an actual delivery, we would be much more interactive. And unfortunately, with a group this size, we pretty much have to keep everybody on mute. I do apologize for that. It is a different experience than from a real classroom environment. And I do have one question already, which is relevant. I have a question: where can I get the presentation PDF? In the email that was sent to you with the confirmation with the login information, there should have been a link to be able to retrieve the PDF as well. And one last logistical thing, I'm getting over a cold, so I apologize for what it does to my voice, and hopefully that doesn't affect the delivery too much. So with that, let's move on and start looking at some of the underpinning technologies behind big data. Before that, just a little moment on what business intelligence analytics is and where it's come from traditionally. And traditionally, the business intelligence and business analytics has been a function that's performed inside enterprises, usually large enterprises, using classic database engines, big database engines that follow a relational model. We'll often hear the term OLAP, or online analytic processing, which is really a term that means the database is optimized for queries rather than transactional processing. But the fundamental technology is still the same as what we use to underpin transactional systems, classic relational databases such as Oracle or SQL Server or MySQL. And we also see organizations using data mining systems which extract data from these OLAP platforms and use it to be able to try and discover interesting things from data. And the concept, the process of data mining is the process of trying to take data and uncover relationships and truths that data expresses that may not be apparent on the surface. So data mining is going beyond simple reporting and simple querying to actually discover new things about data. Now, traditionally, data warehouses, which are the underpinning of a lot of the source of information in a traditional business intelligence and analytics role, are based on classic relational database technologies that have certain rules on how they need to be organized and the quality and properties of the data that are in them. So data is always stored in particular formats. It's stored in tables. These have relationships between them. They're internally consistent. The data has to be complete in the sense that there's no concept of partial data generally. And these systems are designed to be highly reliable and highly available and have a bunch of properties around how data gets into them and how it's managed and the properties that the data warehouse has to be able to adhere to throughout the update and query process. What this will typically look like is something like the architecture that's on the slide here. We have a number of source systems, such as customer relationship management and enterprise resource planning, finance. They're creating data, and this data is pulled out of these transactional systems by some process that we'll just describe abstractly as ETL, or extract, transform, load. And we massage that data to clean up its quality, and then put it into a traditional data warehouse. So organized for queries, but still a relational model. And then it's consumed by a number of different roles. So we have a number of tasks that are specialized for particular things inside this environment. We have an OLAP engine, essentially a database, that's been designed to have a particular structure and summarize data along that structure to support particular kinds of queries. So we'll design the data in the data warehouse, the data in the OLAP engine, with a particular sets of queries in mind. And sometimes those queries are apparent from an understanding of business problems, but sometimes it's not readily apparent what the kinds of queries should be. And then we also have, once the data is in there, we also have the ability to try and do something with it. Now, classically, we can do business intelligence and reporting and simple extract queries. But data mining allows us to go beyond that, to be able to try and discover patterns and relationships in the data that would not have been otherwise apparent. That would allow us to do things like determine, for example, if I'm selling products, what the relationships between different products are and how I can sell them together to maximize profit. To be able to identify clusters of customers, to be able to determine what their attributes are, and maybe determine what makes a good customer versus a bad customer, and therefore be able to target good customers, et cetera, et cetera. And generally, this process of OLAP and data mining is conceptually kind of a pipeline. So you have the data in the OLAP environment, which is pulled out by the data mining engine, and then used to try and find insights. So the OLAP engine, the database, is simply a repository of data. It's an input into the data mining engine. There has, however, been in the last several years a trend away from classic relational databases into this class of databases and class of data storage technologies in general that's got this name big data or NoSQL. And big data solutions are characterized by solutions that take a more relaxed view of how data is stored and how it's manipulated than a classical relational system. And just as a little bit of context, the term big data has come to mean a lot of things and it's come to mean nothing. It's become a bit of a marketing buzzword and a kind of hypey word that makes it a little difficult sometimes to describe what we're actually talking about. But when you're in the field, the concept of big data has really come to mean solutions that are other than kind of classic relational database solutions. So one of the misnomers of big data is that big data only applies to data that's really huge, where you need so much, where your data volumes are so incredibly high that you just can't deal with it with classic relational systems. And that may be true in many cases. But big data, the techniques behind big data apply equally well in situations where you're simply dealing with moderate amounts of information, but you need to be able to do it, or you have an advantage in doing it in a less structured way. So a more precise way of talking about this might be to use the term NoSQL. And NoSQL is a term that's come to mean not only SQL solutions, in other words, data storage solutions that don't follow the standards that people are used to with the SQL, the structured query language that underpins relational databases. And the primary advantage of these is that we have these NoSQL systems that have properties such as lack of strict limits on how data integrity is imposed and how it's enforced, more flexibility in how data is stored, and therefore less data priming required, or less cleanup. The ETL process can become much, much simpler in environments like these. And in particular, an ability to deal with unstructured or semi-structured data in a variety of different formats. And especially the ability to deal with data that may vary in form. I may have data about a particular customer that comes in many different forms because it's come from different sources or it's unstructured to begin with. And I can often deal with that effectively in a NoSQL environment, which would have been very, very challenging to deal with in a relational environment. Now, one of the results of that is that big data solutions can often be scaled to very, very high capacity solutions, effectively with linear scaling. And linear scaling means if I double the number of resources, servers say, in the solution, I double the throughput. And that property does not exist with relational databases. Relational databases, they scale, but generally only to a limit. As you add more servers, they start to have less and less effect. Big data solutions, because they're more relaxed about how data is stored and managed, can scale linearly. Now, the slide says you take that with a grain of salt. That's kind of true. Solutions always have limits, and they often have single points of failure or single choke point. But with the right selection of product, you can select a solution that won't be an issue for you. The big issue, the take-home message, is these solutions scale very, very well, particularly in a distributed environment. And the other advantage that we have with these NoSQL solutions is they're typically supported by a very wide range of external tooling. So additional things that are additional product that's available surrounding them. Now, one of the challenges with a NoSQL environment is it's not like NoSQL. It stands for not only SQL. It's not like there's SQL and then there's one other thing. In the NoSQL environment, there are many different query languages. There are many different ways of talking to the database. And some of these products, they kind of stretch the definition of what you think of as a database. They may be more platforms for managing data. So the way that they actually deal with, the way that you talk to them and the way that they store data and the way that you compose queries can vary tremendously by platform. There is a bit of an effort to try and unify that. We'll talk about that briefly at the end. But the issue of having kind of multiple ways of dealing, very product-specific ways of dealing with data storage and queries will be with us for a very long time. Now, where did a lot of this come from? A lot of this technology came from an algorithm called MapReduce. And this is important for understanding both the history of where a lot of this technology came from. And it's also the basic mechanism that underpins many of the solutions today. MapReduce came out of Google. It was a generalization of some data flow algorithms that were known for a very long time. This is not a kind of new idea, but its application was very new. And what was really particularly interesting about this was it introduced a programming model and a framework for executing that model in a distributed environment. It was extremely powerful. So people think of MapReduce in a number of different ways. They think of it as a programming model or a parallel processing framework, as a computational paradigm. I think of those statements as largely equivalent. Or they think of it as a batch query processor. And because the application of MapReduce tends to be very batchy. And all of those definitions are okay. We'll talk a little bit more about what MapReduce actually is and how it works, and it should clarify why people think of it in these particular ways. The basic concept behind MapReduce came from functional programming languages. And the idea of a map is simply that you're taking data and you're mapping it to a number of different places. So if I have a function, an abstract function, the input of the function is mapped to its output, basically one-to-one. And a reduction is a step that takes several pieces of data and reduces it to a single one. Think of it as a summary. Combining these two functions together allows us to be able to break our computing task into two phases, one of which is transforming the basic elements of data, that's the map, and then one of which is summarizing them, which is the reduce. Again, kind of hang on until we do a little bit more explanation about how MapReduce works, and this will become a little bit more clear. Now, this all started in the early 2000s. It was used by Google as the underpinning technology behind its search engines. It was released as a series of papers and then has been adapted by a number of different players. So the general technique of MapReduce has been reused several times over. And despite the fact there's a patent on it, the technique is very general, and the technique has been re-implemented in many different scenarios by many different players in this space. So how does MapReduce actually work? Well, what we do is we break the computing problem into a couple of different phases. And the first phase, it maps the problem. I'm transforming an individual element of data. And the reduce phase takes a number of different outputs of that map phase, that transformation, and does something to summarize them. And I'm being very generic about what this summarizing means. Now, the thing that makes MapReduce particularly valuable is it allows you to implement a so-called shared nothing architecture. And a shared nothing architecture is one where we take a computing problem and we distribute it amongst a number of different computing resources. We'll call them just servers. And in a shared nothing architecture, those servers don't share anything. They don't have to have common memory or common databases or anything like that, which means they can operate completely independently. And the way this works in MapReduce is each of these map phases is able to be kind of standalone operation. So because of this mathematical property that the map phase takes a single input and produces a single output, generally over and over again, but this is the basic function that it's performing, it shouldn't be much of a leap to see that you could take a very large set of input data, divide it up amongst a whole bunch of different map processes, and have each of the map processes run independently. What does that mean? Well, now it means I can have a large number of servers. Excuse me. I can have a large number of servers which are cooperating because each of them is working on one part of the problem. And that means that the throughput of my solution overall is dependent simply on the number of servers that I have. That's linear scaling. Very, very, very attractive. Another architecturally attractive thing is because they're shared nothing, I don't need specialized hardware. I don't need all kinds of fast interconnects or shared SAN or anything behind them. In fact, I can implement this in cloud. And I can simply spin up additional servers as I need them in the cloud environment. It works very well. Now you're going to say, what about the reduce? The reduce step is actually taking this data and combining it together. There is communication between the servers, and it has to happen with the reduce step because I have to consolidate the data. So it's not like there's kind of no communication between the servers, but it's isolated to the reduce step, or it's isolated to the summarization. So all of this results in this environment that is mathematically really attractive and architecturally really attractive from the point of view of what you actually need to implement it. And here's an illustration of how it might work. I have problem data. I distribute that data amongst a number of worker nodes. Each of the worker nodes is performing map and reduce steps because it can do reduce steps on the data it has locally. The data is going to come back to the master node and will have to be reduced again there if that's what we're doing. and then the final result will go into the solution data. Now, this isn't the best graphic because this is more an architectural thing. It doesn't show the data flow as much, but it's a good illustration of kind of the overall effect of MapReduce. Now, there's a question, and this is an insightful question: who actually does the data partitioning? There are many ways that can actually happen. So let me back this up with a little bit of another illustration of this that might make it a little bit more clear. And I think I'm going to be talking over some of the slides that are coming, but that's okay. So imagine that I have a problem where I'm counting frequencies of word occurrences. In linguistic analysis, one of the things that we look at is which word comes after another word in what frequency. And you can tell things like different authors have different patterns of word frequencies. And I can also use this for predicting, for doing things like correcting text. If I see a pattern of words, and I know that that pattern is highly unlikely, but there's a very similar pattern that's much more likely that suggests that it might be a correction. So this is kind of a useful thing to be able to do. So let's say I go out and I go to some source, and I get millions and millions of documents, each of which are some English language document. And I have a couple of ways I can do this, but the simple way I'm going to do this is I'm going to say, okay, I'm going to have a distributed file system, and I'm going to dump those documents in there, millions and millions of them. And they'll exist in different places in the file system. I probably don't care. The file system is going to distribute them evenly for me. Maybe they exist distributed over 100 different servers. And then I'm going to have a job which goes through each of the files. What the job will do is it will read a file, and it will count the frequencies of words. So somebody said, and then. Okay, so that's one instance of and followed by then. It's going to count those up for the single document, and it's going to emit a file that contains word pairs and the frequency. And it's going to run against whatever documents happen to be on that server. So I've got 100 servers. All the documents are distributed evenly amongst them. What you can see is I've got this mechanism for doing this word counting across 100 servers in parallel. And it just kind of magically happened because of the way I dumped the data into the distributed file system. Okay? So the question was originally, who does the data partitioning? This is one example of that, and this is a very common use case where the data comes in many little buckets, in this case files, and you just allow the distributed file system to allocate them across nodes evenly. Now, let's say that I had actually one gigantic file with all the text in the English language in it. I might have to break that up, and I might have to break it up into chunks. So what part of my data preparation might be to take this gigantic file and say split it into chunks, and each chunk is maybe a megabyte. So I just have this job that breaks it up into individual files, and then I distribute those files. So that's another example of how data partitioning could work. There are many ways it can happen. The nice thing about this is the way the data partitioning is done isn't that relevant for the quality of the solution. Now, let me continue this example for a moment because I'm at the point where I've done a map step, and it's not really apparent where this is going to go. So here's the next place it goes. For the reduce step, what I do is I take each of those files. Remember, each of the file that's an output is a list of word pairs and their frequencies. And what do? I simply merge them together. So I merge them together, and if I see one file says and then occurred 132 times, another file says and then occurred 6 times, the total is 138. Do this over and over again until all the files are merged. I end up with one file that has the word frequencies for everything in the English language. And the thing that I was able to do in parallel was the heavy lifting of actually going through each of the individual files. So that's a practical application, a practical example of how MapReduce is actually used. And I use this as an example because it's relatively easy to explain, and it's relatively easy for people to kind of see what the what's actually going on. But what's actually happening in the real world is people are doing much more sophisticated things, but they're all following this basic pattern. Now, how do people actually do that? Well, there are a few ways that you can do that. We have an illustration, which I'm just going to touch on very briefly because we go into it in much more depth in the actual course. And it's a little bit out of context when we're just looking at this one chapter. But here's an example of how we can use MapReduce in kind of this JavaScript example. And unfortunately, in the course, what we do is we have more introduction to what this means and how it works. But I'll just touch on it briefly. Here's an example of a map function. What this map function is it's taking its input and it's multiplying it by 1.1. It's returning x plus x over 10. And the input is this collection, 1, 2, 3. So the map is producing an output of 1.1, 2.2, and 3.3. What makes it a map? There's a one-to-one correspondence between the data on the input and the data on the output. It's just been transformed. In my previous example about counting in the English language, the inputs, these 1, 2, 3, would have been individual files that contain text. And the output is files that contain the word frequencies in those individual files. The reduce phase takes an input, in this case 1.1, 2.2, 3.3, and what it's doing is it's adding it up. What the reduce function is actually doing is it's taking the first 1.1 and it's adding it to the rest. And this happens recursively, so we get effectively what happens. So we get 3 plus 3 plus 2 plus 2, 2.2 plus 1.1 produces a result. These two operations in sequence, map followed by reduce, have the function of adding up 1.1 times all of the inputs. Now, this doesn't sound particularly exciting, but again, exactly the same principle is applied when we're doing this at a very large scale. The map and the reduce functions might be very, very complicated. So they might be doing some very, very interesting things, but the basic principle is always exactly the same. And that's what makes this so useful. One of the major techniques that people use, major platforms that people use to actually implement MapReduce is a platform called Hadoop. And Hadoop is a particular implementation of MapReduce. It is an Apache project, so it's complete, it's free, open source. And it consists of 3 components. There's a common library, so it's kind of a set of underpinning functionality. Then there's the Hadoop distributed file system, which has some really useful properties about how it manages files in a large distributed environment where it makes the assumption that the underlying environment is not particularly reliable. In other words, it's very tolerant to things like disk failure. And you know, we don't really have the opportunity to go into that more, but it's one of the very valuable properties of Hadoop. And then lastly is the MapReduce engine, which is really the engine that kind of sits on top of the file system and actually performs operations. A Hadoop implementation then can be used for very, very effective parallel processing of particular kinds of data processing jobs. And generally, the properties of those jobs are as follows. They're generally write once in the sense that you load the data into the system. This is not a good platform for kind of constantly updating data. Load it in, do lots and lots of analysis on it. I read it many times. It's very, it makes very effective use of parallel resources, but it tends to be very batchy. So a MapReduce job or a sequence of MapReduce jobs is generally thought of as a batch operation. And at least at its core, it kind of is. What we're going to see is there are solutions on top of that that use Hadoop as an underpinning technology, but provide a much more attractive shell on top of it. This is an example of just some of the particular solutions that build on top of Hadoop, such as HBase and Hive. These are data warehouses that have particular properties, and they're targeted toward particular kinds of data storage and data retrieval. Mahout is a machine learning application, which is actually a set of JavaScript libraries that is intended to be plugged into Hadoop and uses Hadoop as a data repository. And there's an et al. Because this list of things that's built on top of Hadoop kind of goes on for a really long time. There are many, many applications that build on top of Hadoop very effectively. Excuse me. Now, we'll go into a little bit more detail about how Hadoop's implementation of MapReduce actually works. So inside Hadoop's implementation of MapReduce, remember the Hadoop MapReduce engine is a set of functionality that comes as part of the Hadoop package that implements the MapReduce algorithm. And the way it does it is it has an application, a job, called a job tracker, which is responsible for taking input and pulling that into the algorithm that's going to be used. Generally, that input comes from files sitting in HDFS. So when job tracker receives input data, when it recognizes that there's something to do, it manages the execution of so-called task tracker nodes. And the task tracker node is the node that actually, or the server, that performs the map and reduce operations. So job tracker is responsible for engaging the actual resources and telling them what to do. So task tracker will then bring up the particular map and reduce steps that you're actually performing. Now, one of the things that happens here is the map and the reduce step that the task tracker is executing. You could think of as a plug-in component. You have to supply it. So you may be supplying something written in Java. Is a common use case. You may be supplying programs that accept filters. We'll look at that in just a moment. It's a generalized framework that you plug in only the map and the reduce operations. So this points to one of the real benefits of using Hadoop as a platform. You don't have to implement all of this stuff from scratch. You only implement the pieces that are specialized to your particular purpose. Now, the other thing that's interesting about this is job tracker knows something about where data is actually stored. So it knows, for example, the physical location of files in the distributed file system. And it will try to assign those to nodes that are physically connected or close in the network topology to the actual file. So it makes some attempt to optimize the overall efficiency of the entire network. But it also allows the network to be, the overall platform, to be very fault tolerant. If, for example, a task tracker node fails, job tracker can simply resubmit those portions of the workload to somebody else. And if a file isn't available in one particular place because the disk has failed, it can replace that file with another one, a redundant copy from another place. So all the different components of the Hadoop environment come together to produce this environment that's very fault tolerant, highly parallelizable, and doesn't require a lot of specialized hardware. Now, I mentioned that one of the types of jobs can be programs that simply accept input and produce output. Streaming MapReduce is a technique for writing the map and the reduce functions as effectively filters. So if you're familiar with Unix, Unix does a lot of, you can do a lot of work with so-called filters, which is simply an application that reads from standard input. It just reads input, and it produces output on standard out. It just writes it back out. And because of this, the streaming MapReduce libraries can wire these things together. So I have this even better ability to wire up a solution because I can write these, what in the slide is referred to as command 1 and command 2, parts of the map and reduce functionality in anything that I want. It could be a Python program, it could be C that I compile. There's a very simple example here using word count, which kind of follows this model. But it makes it very easy to compose together applications without having to know things like Java and the Hadoop programming interface. And this is particularly valuable for text processing. It's particularly valuable for environments where you're doing things like taking maybe posts from social media and processing it for things like sentiment analysis, because it makes it very easy to compose the portions of the solution together in a very flexible way and allows you to, I mean, the slide talks about it as test-driven development. What they're really getting at is the idea that you can test the individual components, because they're simply command line programs, very easily and rapidly kind of evolve how they work, and then plug them into the MapReduce engine as map and reduce steps to form a complete solution. And I'm not going to try and suggest that this is rapid development by any means, but compared to trying to compose these solutions out of code by hand, this is much, much simpler. I'm going to skip the slide about how you actually set that up, more relevant in the course environment. There are other alternatives as well. So if I don't want to write my map and reduce steps in Java, and I don't want to write them as command line filters, there are a number of other alternatives that are available, and one of the ones that's becoming popular is Pig. And Pig implements a language which, of course, has to be Pig Latin. And what Pig Latin is done is a way of specifying MapReduce jobs in a relatively intuitive way to specify kind of very large operations that you're going to perform in the Hadoop environment, and then execute them as essentially a script. And here's an example. So what this example will do, and this is a fairly simple example, but if you think about the basic capabilities, I could build this into something much larger and much more powerful. In this case, what I'm doing is I'm saying I'm going to define this records as something I get from loading a file, sample text, and I'm describing its structure. I'm saying filtered records come from the records, and they're filtered in this particular way. So I have these verbs, filter, by, and you see it's referring to data in the data set that I've described by records. Excuse me. I specify how to group, and then within a group, how to perform some operation, look up the max temp, and then dump max temp. And what this will actually do is what this script will do is it will look through, read all the data in sample text, and produce an output which is effectively the same as this. Selecting the maximum temperature for each year from a table of temperatures where these particular properties are true. And what this allows you to do is put together these pig jobs that can perform this kind of processing on massive data sets in parallel. Now, the second comment, the second bullet under note, is an important point about NoSQL databases in general. Not all the time, but many times, these NoSQL platforms, Hadoop, the databases that are built on top of Hadoop, are optimal for dealing with what a relational person would say is a table scan. I'm going to process all of the data in the data set. I'm going to use the parallel properties of the solution to be able to do that very effectively. But I'm most efficient when I'm actually going through everything. In many cases, a lot of these platforms don't index. If you think about Hadoop just on its own, or MapReduce just on its own, there's no concept of indexing that we've talked about. That's because there isn't one. And so I can be extremely efficient in using 100 servers together as in a parallel environment to crunch through my textual analysis of millions of documents. But there's no mechanism for me to efficiently say, I only want to see the documents that are authored by William Shakespeare. So it kind of leads to this point that NoSQL solutions, big data solutions, are very effective at certain kinds of problems, but they're not the solution for everything. And in fact, by no means are they going to replace traditional relational databases. Augment, very effectively. Replace, no. And this is one of the reasons. There are many other reasons as well. So this kind of capability is available across a number of environments, so we don't actually even have to build it ourselves anymore. Amazon provides a service, the Elastic MapReduce service, which allows you to bring up a MapReduce environment in the Amazon cloud simply by specifying the resources that you want to be able to use. So I provide MapReduce applications or scripts I define them, and there are a number of different mechanisms for doing that. And again, I can write them as Java programs and simply upload the jars. I can provide pig scripts. There are any number of different mechanisms for specifying what the map and reduce operation is available to be hooked into this framework. The framework depends on Amazon's S3 or simple scalable storage. So I define an S3 bucket, which is kind of a fancy way I'm going to define inside Amazon a place to put stuff, files, and I'll just upload them into that so-called bucket. Think of it as a virtual file system. And I specify which buckets are to be the inputs and outputs. And then allocate compute resources, so the number of servers that are actually going to be performing participating in the MapReduce operations. And the Elastic MapReduce framework will then orchestrate the actual execution of jobs in that environment. It's exactly the same as I described for how we would use Hadoop, except it's available in an on-demand environment, in a scalable cloud environment, where I don't really have to do much to actually provision any of this. It's all just available for me. This sounds wonderful. As an aside, the big challenge in this is when you have very large amounts of data. Let's say you have several terabytes of data you want to go through, and it's sitting on a bunch of servers in your corporate environment. The biggest challenge you've got is actually not spinning up the environment in Amazon. That's easy. The biggest challenge you've got is how do you get those terabytes of data into the Amazon cloud? How do you load them into S3 in the first place? And that's the thing that you can't really just gloss over, because it can become very important. And this is very easy to do. I'm not going to dwell on this, but there's an interface for it, and it's very simple to set up. And what's nice about it is we can play with it using sample applications. And you can play with these samples before actually plugging in your own application. A similar concept is available inside the Google App Engine. So the Google App Engine is a different kind of environment. It's a platform as a service. It provides an environment for actually running applications, running programs that you've built, generally in Java or Python or Google's Go language. And it does something very similar to Amazon Elastic MapReduce, except it's more pre-composed for you, if you will. Because the App Engine environment is one where it's providing a platform for executing applications. Contrast that to Amazon, which is providing a platform for spinning up servers and specifying storage resources. The Amazon environment is infrastructure as a service. It's lower level. The concept here works exactly the same, except there's an assumption that what you're doing in the Google App Engine environment is you're storing data and then querying it in this SQL-like language called GQL, which simply allows you to kind of pull data out of this environment. And it's got these sets of semantics for how you actually compose data together and how you form queries. And it goes beyond what we're going to look at to try and look at how it works. The concepts are very similar to what you do in a MapReduce environment, but the access to data is at a little bit of a higher level. And again, this illustrates or reinforces the notion that there are many different options available, and understanding the basic underlying patterns is important. We can look at how data storage is being handled and the amount of data I've got, what kinds of data it actually is. Again, not really going to go into this in this context, nor am I going to dwell on the actual API for talking to it. This example, and you can look at this later if you want just a flavor of how this works, is an example of how you would actually be talking to the underlying platform. This one happens to be in Java, to specify how you want to extract data and then operate on it. Now, many databases have been built on top of these platforms to implement different kinds of data storage mechanisms that are useful in a number of contexts. One interesting one is this database called MongoDB. And MongoDB is, I'm going to go off the slide a little bit and just kind of talk through this because I think it's a little bit easier. MongoDB you can think of as a container that's used to store documents. Documents are held in collections, so I can say I have a collection of documents that presumably are related to some particular thing. And a document is simply a very general object. It's got a set of fields, and each of the fields has a key value pair. So it's a name, and it has a value. And then I can put kind of anything that I want in it, including things like JSON documents, so I can have structure that I'm storing as well. And excuse me, this notion is very flexible. Inside a collection, the documents can have different structures. They don't all have to be the same. And despite the fact that they're not all the same, I can do some very interesting things with them. So I can do things like say, give me all the documents that satisfy this particular condition on a field. And if that particular field doesn't exist in the document, it'll just ignore that document. And a purist would be horrified by this. How do you deal with relational integrity? How do you do any of those things? How do you know what the structure of your data is? But the other way of looking at it is I have this great advantage because I don't have structure. And this is potentially very attractive. Now, I operate on the MongoDB database in kind of a low-level way. I generally am looking for, I'm performing queries to find one particular instance of a document that matches some particular conditions. So the way I pull things out of MongoDB is I'll do things like I'll operate on a collection to find documents which satisfy a query, and then the projection piece is the things that I want. So if I don't specify a projection, I'm going to get the entire document. If I specify the projection, I'm going to specify what fields within that document I actually want. So for example, I can say I have this collection of documents called transaction history, and I can find those that contain the field year with a value 2000. And you can think of extending this more and more and more to the point where I can compose together what are essentially queries that can do some very sophisticated things. This query at the top of the example is one where I'm querying the employee collection to find documents, individuals, of job level 7, salary greater than 90,000, and I want the results sorted in I think that's ascending order of salary. So you find this, you find the way that you're actually querying is a very different, looks very different from SQL. But the functionality is very, very similar. And in fact, what people are frequently doing with MongoDB is they're using it as a very high-performance data store to allow applications like websites to be querying these documents very, very quickly because it's highly parallelized, to be able to pull data out for things like storing product information, say. There are other advantages of this kind of database that we'll cover in other parts of the course. But why people would want to do this, and I'm going to touch on just one of them now, and one of them is the flexibility. The advantage of being able to have these documents that are many different formats and many different structures, all within the same database, and being able to query them and get the things that I need, regardless of what other things are in there, is very attractive and very flexible. You have to be very careful about how you use it, because the lack of structure can also lead to issues with what's the meaning of the data that's stored. But generally what people find is that this lack of structure actually allows them to be much more flexible and shift the burden of away from all of the data preparation that you typically have to do when you're getting data into a relational environment. And it allows you to be much more flexible in your use of data because you don't have to know a priori before you start everything about the data and how you're going to use it. Huge, huge advantage. Another database I'm going to touch on very briefly, Hive. Hive is a database that sits on top of a MapReduce platform. It's used for, it was originally designed to deal with very, very large volumes of data A log analysis is a particularly good use case for Hive. And it's intended to be more structured than things like MongoDB. But it still give you a lot of the capabilities around parallelism and not rigid adherence to relational models, etc. And the primary purpose for Hive is to be able to take effective advantage of this environment that's very, very highly scalable. And the way it works is it's implemented as a layer on top of Hadoop. So it's effectively, the real core is this piece here, driver, the compiler, optimizer, executor. It's taking requests from the outside world, command line interface or ODBC interfaces, and it's converting them into sets of MapReduce operations which it's submitting to the underlying Hadoop platform. So this is very cool. What the implication of this is I can have an underlying data store implemented in Hadoop, which might be absolutely enormous, far bigger than I could effectively deal with any reasonably cost-effective relational database. And I can still talk to it with something like ODBC. And this is a potentially really attractive capability. Now, I can talk to it native as well. There's a command line language which is modeled after SQL. It's not exactly like SQL because not all the semantics really apply, but a lot of the kind of way that it feels is very similar to SQL. We can see that in this example in the next slide. Create table stats, branch ID, which is a string, and so on and so on. I've got some extra decoration that I wouldn't have in a SQL query. I'm specifying row format delimited fields terminated by tabs. That's because the underlying data store is actually just a text file. So there are things I do that I wouldn't do in SQL. But it looks kind of like what I would actually do in a, more or less in a SQL environment. And that's one of the attractions of Hive. It allows people who have SQL experience to adapt to this NoSQL platform without a lot of rework and without a lot of retraining. That kind of leads to the question. We've explored a number of different ways. We've touched on a number of different ways of actually talking to databases, from writing the map and reduce operations by hand in something like Java, or using something like Pig Latin, or using something like the Hive query language, or the MongoDB query language, which looks a lot like functional language. So isn't there some way that all these things are going? Well, there is an attempt. Oh, sorry, I skipped a slide. I'm going to come back to that in a moment. There is an attempt to try and unify a lot of the NoSQL data access methods. So there's been an attempt to try and create the Uncool specification, which is a kind of SQL-ish specification that's trying to apply the parts of SQL that make sense for traditional, for most NoSQL environments, to have a common query language and a common mechanism for describing how you actually talk to these databases. So the Uncool specification is trying to kind of bring these things all under one roof so that I can talk to MongoDB and I can talk to Hive using a unified language, in the same way that I talk to Oracle or MySQL or SQL Server using SQL. It's all SQL with tiny little variants. That's what we want here. Now, editorial comment, this Uncool specification, I don't see it actually going anywhere. There was a lot of effort around it around a couple of years ago where it really looked like there would be some good weight behind trying to build out this as a common specification. And unfortunately, it doesn't seem to be progressing very much. And I'm not sure it's actually that unfortunate, because it turns out that the way that the databases, that these NoSQL products work is actually quite different. One of the things we go through in the course material, in the 3-day course, is the different variety of kinds of NoSQL databases, NoSQL data stores. Because there are all kinds of different ones that satisfy particular needs, and they're good for particular kinds of problems. But the way they work and the way that they talk about data and the way the very meaning of queries is different in these different databases. So I'm not personally convinced that there is a way to try and unify all of these under one specification. I'd personally like to see more uniformity because every one of them seems to work a little bit differently. But having a single specification, not sure that's really going to work very well. Let me return just a moment to the slide that I skipped over by accident. I showed a slide that talked about how Hive can specify data and how that looks like SQL DDL. Well, here is SQL DML, the data manipulation language, where I'm actually doing operations that really look very similar. So look at this last line. Select branch ID deposits from stats where branch ID is a particular string. That is SQL. So this reinforces the idea that Hive as a platform is able to, for cases that it kind of works effectively in, allow people to leverage the SQL skills they've already got, as opposed to something like MongoDB, where the interface is really very, very different. And for somebody who has a lot of SQL background and no programming background, that's pretty daunting. I'd like to start to wrap up now because it's getting close to 1 o'clock. Just a little bit of a plug for the larger course. We've touched on just a few of the topics that we pull out of the larger 3-day course. And I hope this has given you a little bit of a taste for the kind of material and what we're doing in the course. The larger course has a lot more background, because there's a lot more time, on what the platforms are like and how they work and why you want particular ones and why this whole area of big data and NoSQL is different from relational and both the advantages and the disadvantages of that. We spent a fair bit of time on how you deal with those differences and how you actually would roll out an analytics environment and approach analytics tasks inside an organization. And the other thing that I find quite exciting about this course is there's a fair bit on actual analysis using a tool called R. R, yes, the letter R, is a statistical analysis language that's becoming extremely popular for data analysis. And having a bit of an introduction to it is a really valuable thing, if only to understand the capabilities a little bit. So the course is a really nice broad survey of issues and platforms and technologies in the big data and analytics space, relevant to data analysts, business analysts, people who are looking for something that goes beyond traditional SQL data warehousing and relational technology. I want to thank everybody very much for your time, and I'm going to stay on for questions if there are some questions. I did see a comment that a couple of people didn't find the link to the presentation in the meeting invite. I don't have the ability to resend any of that. I'm just going to make sure that maybe we need to resend it again, but I'll make sure that that goes out to everybody on the webinar. And I do hope that some of you will be interested in looking at the broader course or some of WebAge's other offerings. Maybe I will see some of you either online or in the classroom at some point in the future. Thank you all very much for your time. Anybody who has questions, please enter them to chat. I'll stay on for a few minutes afterwards.